Deep within the hearts of neutron stars, in the high-energy collisions of particle accelerators, and in the first fractions of a second after the Big Bang, quarks exist under conditions so extreme that ordinary matter cannot survive. Studying quarks in these extreme environments reveals not only the limits of particle stability but also the fundamental principles that govern the universe. These cosmic pressure tests push the boundaries of physics, exposing the behavior of matter under incomprehensible densities, temperatures, and forces. Quarks are normally confined within protons and neutrons, held together by the strong force and mediated by gluons. But when subjected to immense pressures or energies, these building blocks of matter can behave in extraordinary ways. In neutron stars, for instance, gravity compresses matter to such a degree that nuclei collapse, and neutrons are packed into a dense, nearly incompressible mass. Under even greater pressures, quarks may no longer remain bound inside individual nucleons, potentially forming a quark-gluon plasma, a state of matter where quarks and gluons move freely, interacting in a hot, dense sea. This plasma mirrors conditions in the early universe, offering a glimpse into the first microseconds after the Big Bang. Creating quark-gluon plasma on Earth requires particle accelerators capable of extraordinary energies. Facilities like the Large Hadron Collider and the relativistic Heavy Ion Collider collide heavy nuclei at near-light speeds, producing temperatures and densities millions of times higher than those in the Sun. For the briefest moments, matter dissolves into its constituent quarks and gluons, forming a fluid that behaves with astonishing properties. It flows with almost zero viscosity, exhibits collective motion, and demonstrates quantum phenomena on macroscopic scales. Studying this exotic state allows physicists to probe the strong force in its most extreme form, testing predictions of quantum chromodynamics and exploring the fundamental limits of matter. The behavior of quarks under extreme conditions is not purely an academic pursuit, it has cosmic significance. Neutron stars, pulsars, and supernovae all involve quarks under pressures and densities far beyond anything on Earth. Understanding how quarks respond to these conditions informs models of stellar collapse, neutron star composition, and the distribution of elements in the universe. Quarks in extreme conditions may even hold the key to understanding exotic forms of matter, such as strange quark stars or color superconductors, theoretical states that challenge our comprehension of stability, density, and quantum interactions. At the microscopic scale, quarks under extreme conditions also reveal fundamental properties of the strong force. Confinement, asymptotic freedom, and color interactions manifest in ways that cannot be observed in ordinary matter. Quarks approach a freedom within the quark-gluon plasma, moving as nearly independent particles, yet still bound by the rules of quantum chromodynamics. Observing these interactions allows physicists to test the limits of theory, understand energy distribution, and uncover the mechanisms that govern particle interactions at the most fundamental level. The study of extreme quark matter also bridges the smallest and largest scales of the universe. By examining how quarks behave in particle accelerators or neutron star cores, scientists can infer the processes that governed the early universe, when quarks and gluons roamed freely before cooling to form protons and neutrons. These studies connect subatomic physics to cosmology, showing that the behavior of the tiniest constituents of matter influences the evolution of galaxies, stars, and planets. Quarks in extreme conditions are, in a sense, a Rosetta Stone for understanding the universe's origin and structure. Contemplating quarks under cosmic pressure reveals the profound adaptability and resilience of matter. Even the building blocks of reality can exist in multiple phases, from tightly bound nucleons to free-flowing quark-gluon plasma, demonstrating the dynamic, ever-changing nature of the universe. These studies underscore the principle that the universe's behavior is governed by both extreme forces and subtle interactions, and that understanding these extremes illuminates the underlying order of all matter. In essence, quarks in extreme conditions are nature's ultimate stress test. They show us how matter responds to unimaginable pressure, heat, and energy, offering a glimpse into the primordial universe, the cores of stars, and the frontiers of quantum physics. By studying them, we gain insight into the resilience, structure, and fundamental interactions that define reality. Quarks under extreme conditions are both a laboratory and a cosmic mirror, revealing the hidden strength, complexity, and elegance of the subatomic world and its connection to the grandest scales of the universe.